So the remainder estimation theorem is based upon the remainder, which says that the absolute value of the remainder must be less than or equal to the absolute value of m times x minus a to the n plus 1 over n plus 1 factorial. The m stands for the maximum value of the n plus 1 derivative. So I'm going to write that in. That's going to be the absolute value of n plus 1 derivative of f at c times x minus a to the n plus 1 all over n plus 1 factorial. Let's say cosine x is approximated by the series 1 minus x squared over 2 factorial. The entire cosine function can be written like this, which is what we learned a few days ago. What I want to do is visualize this cosine function as a third order Taylor polynomial as opposed to a second order Taylor polynomial. So I want to estimate the error when the absolute value of x is less than 0.5. Our cosine x, really, we're going to think of it as a third order Taylor polynomial, 1 minus x squared over 2. I'm going to rewrite the 2 factorial as a 2, which means then we're going to use n equals to 3 because it'll be a third order p sub 3, and also a is 0. If we have a third order Taylor polynomial, our remainder is going to come from which term? The n plus 1 derivative. So it's going to come from the fourth term. So the absolute value of r sub 3 of x is going to be less than or equal to the maximum value of that n plus 1 derivative times x to the fourth power over 4 factorial. Now m. What is the maximum value of the n plus 1 derivative? Now in this case it's a special one because it's cosine. If you have f being cosine x, f prime will be negative sine x, f double prime will be negative cosine x, f triple prime will be sine x, and then it repeats. So the absolute value of the maximum value of cosine is going to be 1. Maximum value is 1. And x is going to be whatever we see here. I want the x to be as large as possible. So between negative 0.5 and positive 0.5, the largest possible x value will be 0.5. Let's do another example. I have the function square root of 1 plus x, and I'm going to approximate it with 1 over x plus 2. I want us to estimate the error when the absolute value of x is less than 0.01. Two things that we need to be able to tell are the order and what we're centered about. So since n equals to 1, we want to find r sub 1 of x. Well, that's going to use the n plus 1 derivative, so in this case, the second derivative of f times x minus a squared all over 2 factorial. I know a is 0, but now I don't know what the second derivative of f is, so we're going to have to calculate it. So over on the side, let's figure out f of x is square root of 1 plus x. So f prime of x is going to be 1 over 2 square root of 1 plus x, and then the second derivative is going to be negative 1 over 4 times 1 plus x to the 3/2 power. Now this has an x in it, and my second derivative in here that I've circled in orange uses a c. So all I'm going to do here now is just write this in, but I'm going to plug in a c in for the x. And here's where I'm going to explain to you guys what the c value is supposed to be. So it's going to be negative 1 over 4 times 1 plus c to the 3/2 power x squared over 2 factorial. Now, the x value that we choose here is going to be found on this interval. So negative 0.01 to positive 0.01. We're going to square it, so it doesn't actually matter which one you put in there, positive or negative, when you square it. And then over here, this c. Do you guys remember from yesterday when I talked about c? C is going to be some number between a and x. And a is 0, and x is either negative 0.01 or positive 0.01. The easiest way for me to explain this and for you to think about it is I need to choose a number in the interval negative 0.1 to positive 0.1 so that it's going to make this derivative as large as possible. So what number can I plug into here to make it as big as possible? Do I want to use negative 0.01 or do I want to use positive 0.01? So what happens when we plug in 0.01? The denominator gets bigger because I'm adding a 0.01, therefore the fraction is going to get smaller. Now if I put in a negative 0.01 into that little purple section there, the denominator is getting smaller, therefore the fraction is getting bigger. So in this case, I need to plug in a negative 0.01. We'll use our calculator and add this up, and we get 0.0000123. Our error is going to be that small. Let's do one last example. I want to use an nth Maclaurin polynomial for e to the x to approximate e to the first power to 3 decimal places. Okay, the first thing I need you to understand, if we're going to be accurate to 3 decimal places, that means we want the error to be less than or equal to 0.0005. Let's first write up what e to the x is. Hopefully you guys know what this series is. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So I want to approximate e to the first power. So I know that's 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. Let me write out the remainder estimation theorem that we have. And here I'm just going to write x because I know I'm centered about 0. And I want the error to be less than 0.005, so I'm going to say that I want my remainder estimation theorem to have a value less than 0.005. X is 1, so that means I'm going to plug in 1 into my x. Now m, remember what m represents again. M represents the maximum value of your n plus 1 derivative. Now for e to the x, the derivative of e to the x is always e to the x. So I now need to know what the maximum value of e to the x is. Can we all agree that e will be no more than 3? Can I safely say that the absolute value of m will be less than 3? So I'm going to plug in a 3 here. And then I have 1 to the n plus 1 over n plus 1 factorial. Again, I don't know what n is, but this 1 to the n plus 1 will go away. This is going to be less than or equal to 0.0005. I'm going to take the reciprocal of both sides, so I'm going to have n plus 1 factorial over 3, and that's going to be less than 1 over 0.0005. Multiply both sides by 3, and 0.0005 times 3 is going to be equal to 6,000. So n plus 1 derivative is less than or equal to 6,000. What n value is going to make that true? 7 factorial is less than or equal to 6,000. Therefore, n has to equal to 6. This means then that e is approximately equal to 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial plus 1 over 6 factorial. If we use this approximation for e, our error using this gives an error less than or equal to 0.0005. You will have 3 decimal place accuracy. So it does not take a whole lot for you to be very, very accurate.